So it's a pleasure to welcome Gabriel Sanoja that I met in Bordeaux a few weeks ago. So he's graduating for MIT, and he works on self-assembly of globular proteins, polymer block copolymer to design materials. And then he got his PhD in chemical engineering at UC Berkeley with Rachel Segelman on the molecularly designed polymeric ionic liquids for electrochemical engineer conversion and CO2 capture and sequestration. And then he moved as a postdoc in Constantino-Creton at ESPCI lab to investigate the molecular damage on the fracture resistance of elastomers. And that's, I think, that he's going to present today. And now he's a tenure at the University of Texas, right? And his current research is in the area of soft matter and polymer physics and on the mechanochemistry to engineer soft and tough recyclable materials. So I will give you the floor. Thank you.
Okay, so maybe that's better. Okay, so the story I want to tell you today is actually a lot of the work that I did during the end of my postdoc, those COVID days. And it has to do with some molecular insights on the lifetime of soft materials, elastomers, and how they fracture. So basically soft materials basically are pervasive in society. They're pretty ubiquitous. And here I'm just listing some examples that are very familiar to all of us. You can find them as elastomers, particularly rubber tires and seals. And these are pretty old school applications, but still pretty useful. Biomedical hydrogels, mainly superabsorbent diapers, or more recently contact lenses. These are just still networks that are swollen, and they can also transport small molecules like drugs. So they have attracted a lot of attention too. And another one that is very common is pressure sensitive adhesives. That also date to the early 20th century. The post-it note is a classic, or your regular Band-Aids. And what really makes all these soft materials particularly interesting for society is that they can actually sustain large deformation because of their molecular structure. Okay. So because they can sustain large deformations, for a long time, really, the fracture mechanics community and the polymer community, they have really thought about how do you actually make these materials resistant to fracture. It's a pretty natural question to ask because you are going to apply a very large deformation and you don't want that your material to break. And the typical experiment that you would conduct to characterize the fracture energy and the fracture toughness of this material is that you introduce a pre-crack that you think about as a structural defect into your system. And then you deform the material at a constant velocity. Here in the bottom, I have a video of how that would look like. So you have a pre-crack in your specimen, your elastomer. And this is an experiment that I conducted in ESPCI that I will get to in a bit. And then you see your crack grow. And eventually you reach a point where the material fades catastrophically. And while you conduct that experiment, what you do is you record the stress and the stretch. So here what you have is the stress stretch curve. And eventually you reach a critical point at which the system fails. And then what you can do is that you can actually integrate this curve all the way to the fracture point to calculate what we call the strain energy density, which is a measure of how much energy you're storing the material up to the fracture point. And then you multiply that by a geometric factor. In this particular case, it's the spacing between the clamps because of the geometry of the system. And then you get a critical energy release rate, which is a critical amount of energy that is released to when you propagate your crack. Okay, so that's a typical experiment that you do. And again, it's an experiment that takes the material all the way to the fracture point. It's a Griffith criterion. Correct. So you get like apply a given critical energy to the system, and when you're above that critical energy, the system fractures. Now, in reality, polymers and elastomers don't really go all the way to the fracture point during normal conditions. Most of the time, the system actually goes to very, very low deformation for an infinite number of cycles. By infinite, I mean something very, very, very large. So instead of taking the material all the way to the fracture point, instead you go through many stress strain curves or many cycles of loading and unloading. And because the system is very elastic, it's an elastomer after all, you have basically superimposing loading and unloading curves, meaning that all the work that you do to the system and all the energy that is stored, you can recover it. And that's the beauty of an elastomer, right? But when you actually have a pre-crack or a defect in your system, we all know that eventually it's going to break. So now the experiment is slightly different. Instead of taking the system all the way to the fracture point, what you do is that you cycle it for many, many, many cycles at very low deformations. So here is a video where each frame that you see in the video corresponds to about 5,000 cycles. And you see, your crack is going to grow slowly, okay? And that's actually the question that I'm trying to understand in this talk, or one of the questions that I'm hoping to address over the next minutes is, when you are in a subcritical point, where you are below that critical point that it requires to go to fracture, you can still define an amount of energy that is going into your system, a G, energy release rate, but it's subcritical in nature. So what actually is the mechanism that drives that fracture in a subcritical condition? How is it different from the case of the critical condition? And how can we understand how to design materials to be resistant to fatigue, cyclic loading, as opposed to monotonic loading and toughness, okay? So when you conduct that experiment, you can do it at different levels of G or at different levels of deformation. And what you actually record is the crack growth per unit cycle. So this is, you can think about it as your velocity. And then you have basically three regimes. You have a G0, which is a material property, which people call it the fatigue threshold, at which the deformation or the amount of energy that you apply is so low that the crack effectively doesn't move, okay? At the other end, you have your GC, which is effectively the regime of the toughness, at which you open the crack so much that the crack catastrophically fails, and that's what I consider in the first slide. And then in between, you have a power law that people call Paris law, at which basically you have an increase in the crack growth rate with the applied G. Okay, so that's what you would measure, and that's the macroscopic behavior that you would probe in the system. This is not new. This is a problem that dates to the late 1960s in rubbers, and it actually even older in metals. And basically, this is the data from Lake, Gent, Rivling, many people in the late 1960s, where again, you have a critical condition, you have a power law, and then you have your catastrophic failure. Now, why are these materials elastomeric in nature? And now I'm hoping to provide a little bit of a molecular view of basically what's responsible for this fracture process and what do we understand about fracture from a molecular point of view in order to build a molecular picture of fatigue. What we know is that basically they're polymer networks, and depending on the level of cross-linking and the amount of defects and the amount of solvent, you can control the mechanical properties of these systems. So if they're very weakly cross-linked and highly entangled, they're very viscoelastic, they're more adhesive in nature. If they're well cross-linked, unentangled or entangled, you can idealize this schematic as you want, but these are more elastomeric in nature. And then if you put solvent, you are in a situation where you are a gel, organogel, hydrogel, depending on whether the solvent is water or not. So what I'm going to be focusing upon are systems that are like this. They're well cross-linked. They have defects for sure. It's an ideal picture again. And I want to discuss what is the molecular picture behind them that leads to fracture. And what we know is that basically, even if you apply a deformation that is very low away from the crack tip, you have a stress concentration next to the crack tip. And the molecular picture that we have built since the late 1960s by Lake and Thomas that governs fracture is basically summarized in this schematic. The idea is if you want to propagate a crack, the minimum that you have to do is break a monolayer of polymer chains. So it's a minimum amount of energy that you have to pay in order to grow that crack. And basically, that's defined as this G0, the fatigue threshold that I was referring to before. And it scales with basically the chain length, or the number of monomers that you have in between the crosslinks, or the number of carbon-carbon bonds, the energy of each one of those bonds, which is this UB, and then this sigma 0, which is the density of chains that you would have in a fracture plane. Okay, so this is the Lake and Thomas picture. And again, I'm going to come back to this. It applies to a single layer. So you have to only break one layer of polymer chains at a fully stretched configuration in order to propagate that crack. This picture is highly ideal because in reality, things are more complex. In reality, you actually have a damage ahead of the crack tip, but you can also dissipate elastic energy by other mechanisms. And one that is very common is friction, because we know polymers have dynamics that are important too. And you have these chains that, they can basically slide against each other. You have a friction coefficient. We call that viscoelasticity sometimes. And effectively ahead of the crack tip, you can have molecular damage, but actually a lot of the contributions also come from viscoelasticity. And the consequence of that is a fairly well-known observation, is that as you fracture your material at different velocities or at different temperatures, you can actually get differences in the fracture energy because your system is more or less viscoelastic. Okay, so basically what that has enabled us is to have this empirical description of the fracture energy, where you have a G0, which is effectively all the damage that I was referring to before, or again, your Lake and Thomas limit. And then you have a function that is a function of basically AT, which are your viscoelastic shift factors, and the crack velocity. And effectively that accounts for the friction or the viscoelasticity that you require to dissipate elastic energy. Very recently, work coming out of Constantino's group has shown that the situation is a little bit more complex in the sense that these two things are not necessarily decoupled. As a matter of fact, they are coupled. And that when you are in a situation in a limit where you have low viscoelasticity, you have low damage because the crack tip opening displacement or the local deformation ahead of the crack tip is very small. Whereas when you have very high viscoelasticity, your crack is more blunted, you have a larger damage zone, more friction. So in reality, things are not as simple. You actually have coupling. Okay, so this is what we understand in terms of energy dissipation. Again, when you monotonically load your system and you fracture by crack propagation. In fatigue, things are a little bit less understood. And what I'm hoping to show in this slide is effectively that they are so poorly understood that we don't really understand how to design. So what do I mean by that? So in here, I'm showing the data, the fatigue curves for a family of soft materials, many of them that are sort of well known. These are tough gels developed by Jig and Suo's lab in Harvard. And the fracture toughness of these systems under very specific conditions are very similar to those of natural rubber. This is what I'm indicating with this dashed line. But the fatigue behavior is very, very poor compared to that of natural rubber. So natural rubber is right here. So effectively what you see is that you can have two systems that have under very specific conditions, very similar toughness, but they have very different fatigue resistance. The second observation that I'm hoping to show in this slide is that if you had elastomers, like for example, SBR, which is a classic synthetic elastomer, styrene butadiene rubber, and you have natural rubber, the fatigue resistance of these systems is intrinsically larger than that of the gels, even though, for example, SBR has a lower fracture toughness than these gels. Okay, so it really seems that, we understand that you need a lot of energy dissipation to make systems to be tough, but maybe energy dissipation is not really the metric that you want for making very fatigue resistant materials. Maybe there is something else, because clearly toughness and fatigue resistance are not necessarily very well correlated. And that's the questions that I'm hoping to answer today. What about fatigue resistant, and how do we think when we design, how do we think about designing materials that last a long time? And to answer that question and get some fundamental insights on that, I'm going to use this model system, which are referred to as double network or multiple network elastomers. These are systems that are inspired on the multiple network hydrogels of Jumping Gong in Japan. They were developed in 2003. And it's pretty much Costantino's, if any of you know Costantino, this is sort of like his toy model system for the past decade or so. But anyways, the idea is that you have a filler network, which is highly cross-linked and brittle. So you basically cross-link your network a lot. You make it very brittle but stiff, high modulus, and you have a fracture energy. You have a good order of magnitude. It's about 100 to 100 joules per meter square. And then you interpenetrate that with a very soft and very poorly, loosely cross-linked matrix. And when you interpenetrate those two under very specific volume fractions, you can get into a regime where you have a system that is both stiff and is tough with a fracture energy on the order of 2000 joules per meter square. So this is sort of the molecular design. And the reason why it's kind of interesting is the following, because you can actually have near perfect elasticity all the way to fracture. So what I'm showing here is effectively many, many cycles that have applied to a system of loading and unloading. And what you can see is that the system superimposes all the way to the fracture point. You don't have any viscoelastic dissipation. The system is pretty much perfectly elastic all the way to a fractured point while being tough. And that's not very, very common. In general, systems that are tough are viscoelastic. So this is a system that is tough, but is elastic. And the other neat thing is that it has been shown in this seminal paper, again, coming out of Costantino's group, is that if you actually image the crack tip, or if you actually image the bonds that are breaking ahead of the crack tip during crack propagation, what you actually see is that when you go from a molecular design of only a cross-linked filler network, so basically just network number one, this one, you don't have a lot of damage of the crack tip. Everything is localized. But when you start interpenetrating the networks, you see that your damage ahead of the crack tip keeps growing, meaning that you actually dissipate more energy by damage as you interpenetrate one network with the other. So what is very neat about this model system, two things again, it's nearly perfectly elastic all to the fracture point, and a lot of the energy dissipation that occurs of the crack tip is because of bond breakage of the filler network. Okay, so if I can actually probe bond breakage ahead of the filler network, then I can actually probe directly energy dissipation in a system that is perfectly elastic. And that's actually the experimental design that we implemented. We had a system which is elastic in the bulk, so very far away from the crack tip. If I apply very low deformations, the system is behaving like this, perfectly elastic, and very close to the crack tip. I'm going to have an interplay between friction and damage, and I'm going to try to image what this damage is going to be in order to get a measurement of how much energy is dissipating during fatigue fracture. And the technique, on the reason why we can actually see the damage, because it's not very common that you can actually see the molecular damage, is because I have some training in polymer chemistry. And what I did is that basically I took these mechanophore molecules, which are these probes that were developed by Rinsich-Besma group in TU and Eindhoven. And what's very neat about these probes is that when you actually apply, or when they actually experience a molecular force that is on the order of the energy it requires to break a carbon-carbon bond, they undergo a retro-Diels-Alder reaction. And what's very neat about retro-Diels-Alder reactions is that they always give you some sort of like conjugated group at the end that it can be a fluorophore under a confocal microscope. So when I actually incorporate these probes only on the filler network of my multiple network elastomer, I can actually then probe groups that have been broken and that are activated under a fluorescent microscope in my specimen after it fractured. So the name of the game is, let's make these fluorescent cross-linkers, we put them in the multiple networks, and then we fracture our material, we put it under a confocal microscope, and then we can map and quantify how much damage I had during the fracture process, okay? So here, what I show here in the bottom is an image of how one of those, for example, images on the deconfocal microscope that are obtained. And you see, for example, here, these regions of fluorescence, and this fluorescence right here indicates that you had, for example, a lot of molecular damage. You can see one that is slightly less fluorescent here on the bottom right. And then if you do some nice quantification that I'm going to talk about, you can find your crack edge, and then you can start integrating along the crack edge to actually start getting a metric of how much damage you have. So the first observation that I want to show you, let me see how I'm doing time, is the following. Is effectively what I'm showing here is well, how do these systems behave at the macroscopic level? Let's first try to see how do they compare with the other systems that I presented before. So in orange here are my double network elastomers. And the first observation that we think it's very interesting is that, well, even these double network elastomers, my fatigue threshold, or effectively the minimum amount of energy that I require to grow a crack during fatigue, is pretty high. In general, elastomers are synthetic in nature, historical, natural rubber, styrene butadiene rubber. They have fatigue thresholds on the order of 100, 150 joules per meter square. Gels even lower. Our system actually has a fatigue threshold of about 550 joules per meter square under 400,000 cycles of cyclic load, meaning that you actually have a pretty fatigue resistant material. So the first observation that we have is that these architectures are actually pretty fatigue resistant, and they're still tough. They have toughness that are comparable to that of styrene butadiene rubber. Now, let's get to the damage part. Okay, how much were they damaged and how do we quantify them? Again, what we have is a stack of images that we collect under the confocal microscope. And what we do is that we image on about 1 millimeter or 1,000 microns on this direction. And then we image on about 150 microns depth on our elastomer, okay? And then when we collect this stack of images, what we can do is we can either integrate each voxel or the intensity of the voxels in 1, in 2, or in 3 dimensions. And that enables you to obtain a damage profile. If you integrate in 2 dimensions, you can obtain a local map of damage if you integrate on 1 dimension. And if you integrate on 3 dimensions, what you just get is an average of all the damage that you have. And I will show you examples of the profiles, of the maps, and of the averages in a second. But if you want to see actually details of the quantification, you can actually find them in the paper. So the first observation that we have is that, okay, if our system actually fractured, this is our fatigue curve. So this is a macroscopic observation. And what you have here is the molecular damage. The molecular damage, we're defining it as the number of Lake and Thomas monolayers that break. So we actually do some rescaling of our intensity. And effectively what you have here at 1, this is your Lake and Thomas limit. So what we're showing here is that as you increase G, or as you increase the stretch at which you cycle your system until fracture, you actually break more monolayers of polymer chains in order to propagate the crack. So this is direct evidence that the Lake and Thomas model that has been around since the 1960s is insufficient and incomplete to describe the amount of energy that you dissipate by network chain scission. Because you don't only break 1 monolayer, you actually can get to break up to 100 monolayers of polymer chains before you actually propagate that crack. And that number of monolayers that you break is actually a function of the stretch that you apply during your cyclic load. Okay, so that's one of the second conclusions that I wanted to show you. So if I want to boil this down to a scheme, effectively what you have is that at very low deformations, you have low damage, and I'm indicating that with a yellow color. And at very high deformations, your crack tip is more blunted, and effectively you have more damage, which I'm indicating with the red color when you get to the fracture point. So again, Lake and Thomas picture incomplete because your damage depends on the stretch that you actually apply to the crack. Now, this is for one system, but what we think is kind of interesting is to try to understand what happens in terms of molecular design when you start considering multiple architectures. And to do that, I'm considering now 2 double network elastomers. So these are 2 double network elastomers, and they have a different cross-linking density on the filler network. And what's very neat about this system is summarized in this plot. Effectively, your elastic modulus is the same. So the bulk of the material that you cycle around this regime is pretty much the same. It's not changing too much because, again, fatigue occurs here. Fatigue is a 10–20% deformation. So these systems have very, very similar elastic properties, but the strain hardening and the fracture energy are different. Okay, so we have a model system in which we have the same elasticity, but different properties at large strain. And what we wanted to understand is, okay, if we have systems that have different differences at large strain, how does that change the fatigue behavior, even if the elasticity is the same? And again, the macroscopic observation is already interesting on its own, in my viewpoint. For example, what you see here is that the system in red is actually tougher, meaning that it's more resistant to crack propagation when you apply monotonic loading, but it actually behaves poorer in fatigue. It's not as fatigue resistant as a system that is more brittle. Okay, so we thought that that was interesting on its own because it's showing us that toughness, again, is not a good metric for fatigue resistance, and systems that are tough are not necessarily good under cyclic loading. And the second observation, which is more molecular in nature, is summarized in this plot. Again, I'm only focusing on the average. And what you see is that on average, when you apply and the data is very, very scattered, and I acknowledge that, but basically what it seems to be happening is that the systems that are more fatigue resistant actually undergo less damage than the systems that are actually tougher. The red system seems to be always more damage ahead of the crack tip when you fracture them at the same level of G. So when the amount of energy that you apply to that crack is the same, effectively you have more damage. And the reason is actually summarized in this, or we think it's summarized in this picture, in this scheme once again. So now if you compare two systems at the same G, okay, because this system is actually tougher, effectively your crack tip opening displacement, or the local stretch ahead of that crack tip, is going to be larger on each cycle that you apply. So effectively what that means is that because you have a larger stretch ahead of the crack tip, the probability of breaking a polymer chain ahead of the crack tip on each cycle increases, giving you more damage and lower fatigue resistance. So again, I hope that this scheme sort of summarizes the big picture of what's going on. At low stretches, if you have a strain hardening system, effectively you have low damage. As you increase the stretch, the damage increases. And if you actually make the system to have a lower strain hardening or more stretchable, then you actually have more damage and lower fatigue resistance. In reality, the situation is slightly more complex, and I unfortunately don't have time to talk about it today because I want to get to something else. But I'm happy to discuss further if you are interested. Effectively, what we see is that very large deformations, you can access a regime where your fracture is really, really catastrophic and really fast, but the damage is very low, but it's very highly localized. So I'm happy to discuss this further later, but basically it's a little bit more complicated. It's not only about the magnitude of the damage, it's also about the localization in terms of a characteristic length scale ahead of that crack tip over which that damage is concentrated. Yeah. Yeah.
Is it now, so in the bulk experiment, failure, is the stress that you have there comparable to the stress at the tip if it propagates? Because it's a localized stress. Is it comparable or is it different scales?
I mean, it's larger. The stress, there is a stress concentration ahead of the crack tip. So that's the question. What is the local stress and what's the local stretch?
Is it the same physics in both cases, or is it a different thing?
So
that's what I want to understand, the scale of stresses.
So I think the physics is similar in the sense that when you start damaging the system ahead of the crack tip, you start homogenizing that stress concentration. So in my viewpoint, really what ends up giving you fatigue resistance is that you have initially a stress concentration. When you damage the system, you locally soften. And if you manage to stabilize the stress ahead of the crack tip and make it similar to the stress in the bulk, then you don't have a driving force for fracture anymore because of your Griffith criterion. After all, the Griffith criterion is telling you that you need a stress concentration to propagate the crack. If I locally damage the system and I soften locally and I create a stable state where everything is homogeneous, then I don't have a driving force anymore. Now, how to locally soften over our area, depending on the molecular design of the structure, that's the trick. And I mean, we think that this system is slightly better because it's strain hardened, but yeah, that's pretty much all I can comment for now. How are we doing with time? All right, I have some time. So this is what I showed you is on cyclic loading. What about toughness? Can our technique actually capture the physics that we understand for toughness? I think the answer is yes. So what we have here is the images or the stack of images that I collected when you actually propagate your crack monotonically, okay? And what you can do is you can generate maps. So these are maps of damage. So basically what you see here is that if your images are homogeneous in nature and it's slightly more fluorescent ahead of the crack surface here or ahead of the crack surface here, what you obtain are homogeneous maps. Okay, so you have a map that of damage that is homogeneous, and then in this particular case there are some heterogeneities. So you start seeing some heterogeneities as you move down into your system. But here on the upper right, what you have is the profiles. So effectively, if I integrate my damage along this direction and along this direction, what I can have is a profile of how much damage do I have away from the crack surface. And what that enables us to do is basically get a characteristic length scale of over what distance is my damage concentrated, and effectively how much damage do I have. So this is similar to what I did in the fatigue case, but I think this is more illustrative to show the potential of the methodology in terms of three-dimensional space. But the physics that arises from this is the following. The system that is tougher, which is the red one, actually has more damage as measured by the integral under this curve, and that is summarized in this number here. So effectively, what this is telling me is that I need to break about 150 Lake and Thomas monolayers to propagate my crack in the system that is very tough. And on top of that, that damage is delocalized over a large length scale, a length scale of about, I'm taking the L1/2. So effectively, when does this peak decreases to 1/2, it's about 130 microns. You can define the length scale of however arbitrary way you want. But effectively, the physics is the following. If you have a tough system, you need a lot of damage delocalized over large space. And that's the physics that Rivlin, Thomas, and that we have known for decades. Whereas if the system is more brittle, you have less damage localized over a lower length scale, in this particular case, about 30 microns. So summarized here in this scheme, systems that are tough, you have large damage over large length scales. Systems that are more brittle, you have lower damage under lower length scales. So our methodology captures the physics that we knew about toughness, but it also brings us new physics about fatigue resistance and durability. So the takeaway messages that I want to give you in this first half of the talk are the following. The first of all is that macroscopically speaking, already this architecture of interpenetrating double networks, it has a pretty good fatigue threshold. It already has a fatigue threshold that is about a factor of 5 larger than of conventional synthetic rubbers like SPR or natural rubber. Natural rubber is not synthetic, but it's a traditional rubber. The second observation or point that I want to take away is that really your damage increases with the amount of stretch that you apply. And this goes against the conventional picture of Lake and Thomas, where the damage is said to be that of a monolayer. In reality, you break more than a monolayer, and that depends on the local stretch that you apply, or the G or the lambda to the crack tip. And the final point that I want you to take away from this section of the talk is that if you have a strain hardened system, that gives you a more stable damage zone, in the sense that you have a lower crack propagation velocity at the same G. And that is not really good for toughness necessarily, because that means that you have lower damage over a lower length scale, but it actually gives you a more stable damage zone under fatigue resistance because of what we were discussing before, because it gives you a homogeneous stress distribution, and that enables you to make more durable materials at the expense of the fracture energy. So with that, I want to spend the last 15 minutes of the talk talking about another problem, which is that of cavitation, which is also an old problem in polymer science and in fracture mechanics, and that we thought that with our methodology that we developed, we could also bring new insights into physics of why do materials break. Before I consider elastomers, now this is the case of a seal, which is another big application in soft materials. So the experiment, this is called cavitation due to rapid decompression. And the idea is that you have a supersaturated media and you quickly drop the pressure. And when you quickly drop the pressure, you have an imbalance in chemical potentials. So your chemical potentials need to balance again because of a thermodynamic driving force. But the issue is that your diffusivity inside your media is very low and you are supersaturated, so you nucleate bubbles. And you need to get rid of those bubbles, and those bubbles eventually disappear until you equilibrate your chemical potential. In the case of a liquid, that's a classic case of a champagne or any carbonated drink, a soft drink. You open it, you hear your psst, and then you have your Le Petillon, and then the bubbles, and that's called good. When you have a soft material, the bubbles are not necessarily so cool. And the reason being that they can actually induce damage. So for people that do diving, This is a well-known fact because you cannot get out of the water very fast because then you have rapid decompression and then you can have permanent damage. And in the case of seals, this generally leads to the phenomenon that we call rapid or explosive decompression. So this is an image of tissue that is damaged because someone was diving and got out of the water too fast, and that's completely reversible. And then there's an image of a seal that broke because the pressure was dropped too fast and effectively breaking your material. It's a pretty old problem. It's a problem of cavitation. It was considered by Alan Gent again in the late 1960s. So again, old science. And the idea is that you have a cavity or a bubble inside a media, and then effectively you apply a pressure within that media, and then you have a pressure balance. So your pressure effectively inside the cavity has to be balanced by the external pressure. Then you have a Laplace pressure that comes from the surface energy of the bubble. And then you have the elasticity, that is retractive force that is intrinsic to a soft material because of its polymeric network structure. Okay. Now, this problem was solved by Alan Gent in the late 1960s, and he considered the case of a neo-Hookean elastomer, meaning that the system can stretch infinitely. We know that it cannot stretch infinitely. We know that it has a limiting extensibility, but it's a pretty common approximation in fracture mechanics. And the second thing that he did, that he neglected the surface energy because the surface energy is not very large in these systems. And he got this very famous result, which is effectively that your critical pressure for cavitation is effectively scales with the elastic modulus or the shear modulus. So E here is the Young's modulus, nu is the shear modulus by a factor of 5.5 or 5.6, etc. So this is a criterion that is completely governed by the modulus, which is a low deformation property of the elastomer. Okay. Now, this is the data from Gent. It seems to do a pretty good job for conventional elastomers. So this is natural rubber, and here his theoretical prediction. And for the most part, it does a pretty good job. Like the systems here that are black dots are systems that didn't cavitate, and then you start seeing that as you move away from your theoretical prediction, you start seeing cavitation in this open cylinders. Okay. Now, again, it seems to experimentally work for conventional elastomers, but there is theoretical work by Williams or Shapery, which basically they say, well, but you know, the system cannot be neo-Hookean. It has a limiting extensibility because of your Lake and Thomas argument. You have polymer chains. Polymer chains have limiting extensibility. So this criteria must be insufficient. And this created a debate that you're welcome to go read throughout the 60s, 70s, 80s, because theoretically the prediction was that this shouldn't work, but experimentally it kind of works. So we have always this, you know, theory versus experiment story. So what we figure we would do is, well, can we actually use our multiple network elastomers to bring new physics into this problem? And here is just a slide that summarizes how we make this. So we take a single network, this is a cross-link network of ethyl acrylate, and then we swell it with more ethyl acrylate, we polymerize a second network, then we swell it with more ethyl acrylate, and we polymerize again. So we have these interpenetrated networks once again, which is our model system. And the reason why it's our model system is similar to the case of fatigue. The reason is the following. If I actually do that, I get 3 different systems that have the same modulus or pretty similar, you know, 1, 1, 0.9, 1, 1.5 megapascals. So the elastic properties are very similar, but the large deformation properties are dramatically different. You have different fracture toughness. You go from about 100 joules per meter square all the way to 3,800 joules per meter square. So we figured this would be a good model system to try to bring some new physics into this discrepancy between theory and experiment in the case of cavitation. So here is the experimental data. This is the same experiment that was done by Gent. We actually measured the critical pressure for cavitation. Here is the theoretical prediction, this dashed line. And now we see that it doesn't really work very well. We see that you can actually have systems that are, you know, like if the system is very brittle and your modulus is very low, your criteria seems to work okay. But when you start going to systems that are very tough, well, things start diverging significantly. And, you know, this is the plot, but I always feel like pictures are more effective way to convey information. So here what you have are the pictures of these 3 minimum pressures at which the system cavitated. What you see is that at very low pressures, about 10 megapascals, effectively this elastomer completely bursted. It explosively decompressed. Whereas as you start becoming more tough, you start seeing more controlled bubbles. You start seeing, in this particular case, very small bubbles too, and less of them too. Okay, so it seems like the observation is that if you make the system tougher, you also make it more cavitation resistant. Now, we have our methodology. So can we say something about the fracture mechanism using this technique of mechanochemistry? So the name of the game was very similar. Again, I use my polymer chemistry. I make my mechanophore. I put it in the filler network of my multiple network elastomer. And then instead of fracturing by cyclic loading, what I do is that I apply my explosive decompression. I drop the pressure. I can record the cavities as they grow and decompress. And then I can take my elastomer at the very end, and I can put it under a confocal microscope and map the damage. This was done in collaboration with Sylvie Castagnier in Poitiers. So here is basically what you get from the experiment macroscopically. You drop the pressure at 0, then your cavities grow, and then eventually they disappear, and your elastomer looks as pristine at the very end of your experiment. So, I know from my video where I had bubbles, and I can take my elastomer after I completely decompress it, and it looks pristine, but I can put it under a confocal microscope, and I want to show you how that would look. So when you actually take it under the confocal microscope, what you can see is that effectively everywhere there was a bubble, there is actually activation of the mechanophore, meaning that you have damage because of polymer chains that are breaking at the molecular scale. You can do that over many regions. So any region that you choose, any bubble that you choose, when you take it under the confocal microscope, you can start seeing that you always have molecular damage because of polymer chain activation. So we actually chose one cavity which fortuitously, luckily aligned very well with the direction of the imaging. And we took it our confocal, which is not a very good confocal. We don't have a very good resolution for reasons that I can discuss later. But effectively, we push it to the max. And what we saw is that it would seem that you have many cracks nucleating from a common nucleating site. It seems that you nucleate a bubble, and then you have many regions that are propagating heterogeneously from that nucleation point, similar to a flower. The flower is just basically a schematic to think about it. But effectively, you have, this is more or less the history that we envision for this system. The system is very brittle, so we nucleate a bubble, and then from that bubble, the system is too brittle that many cracks propagate from it, leading to unstable growth and thin penny-shaped damage zones with very heterogeneous fluorescence. If you go to the tougher systems, the situation is slightly different because now your bubbles are more homogeneous because your system is tougher. So what you see at the molecular scale is that now you don't have these heterogeneous fluorescent regions, but they look more homogeneous. We think about them as serials, where effectively, you have the picture that we depict is the following. You create a bubble, but because the system is tough and it can actually resist crack propagation, effectively the bubble starts inflating while damaging the region around it, but it doesn't propagate with multiple cracks, giving you homogeneous fluorescence. So the takeaway messages that I want you to take from this second part of the talk is that the architecture of these multiple networks is pretty cavitation resistant, actually more cavitation resistant than conventional elastomers like styrene butadiene or like natural rubber. And because of the toughness of these systems, you significantly deviate from the theoretical criteria of Alan Gent in the late 1960s. The second point that I want you to take away is that each one of the cavities that you nucleate in this explosive decompression process actually is associated with a very thin and planar damage zone. And we think that that's because you have a penny-shaped crack that is growing in this process. And effectively, that if you use these sacrificial bonds or this multiple network architecture where the filler network gives you toughness, you actually can go from systems that are very unstable and brittle, where you have multiple propagations of many cracks from a nucleation point, to systems where you nucleate the cavity but are sufficiently tough to resist fracture and give you more homogeneous damage zones. So with that, I will thank my collaborators, Xavier, Jean, Matteo, and Josh, who were all very helpful in the quantification process or in the conduction of experiments in fracture mechanics. Sylvie, which was extremely, extremely helpful at doing all the experiments on explosive decompression in Poitiers, and Costantino for all his guidance and mentoring during this work. I thank you once again for your attention, and I'll open the floor for any questions. Yeah.
Thank you. Thank you.